Hi, my name is Minji Jang, a PhD student at UCL. In this talk, I'll present a new benchmark environment for common sense reasoning and RL agents. This is joint work with some wonderful collaborators at UCL and Oxford. I hope this talk will get you excited about incorporating common sense knowledge with reinforcement learning, as well as get you excited to play with our new environment. Many real-world tasks require the ability to quickly adapt prior knowledge to generalize to new situations. People are incredibly good at this, largely by relying on common sense knowledge, that is, common facts about entities and relations in the world. For example, without this ability, a new robot butler might have to turn your kitchen inside out just to fetch you an apple, as it lacks the common sense that apples are likely found in the fridge. While previous work outside of RL has shown that language data and knowledge graphs can be used to assist common sense reasoning, the integration of common sense knowledge with RL models remains relatively understudied. We believe this is largely because common RL environments don't directly enable such research. For example, games like Go involve only abstract entities and rules, requiring no real-world semantics. On the other hand, less abstract environments like StarCraft lack annotations useful for grounding actions and observations to language, while also being expensive to run. To address this need, we introduced WordCraft, a lightweight text-only environment based on the crafting game Little Alchemy 2, whose recipes are based on common sense relations. In each WordCraft episode, the agent is presented with a table of starting items and tasked with creating a goal item, in this case, paper plane, by combining the starting items. WordCraft contains 700 different items and over 3,000 single combination, or depth 1 recipes, where a recipe is a combination of two items producing another item. The task depth is the minimal number of successful recipe evaluations leading to the goal. And since items are represented by words, grounding observations to text is not an issue. The agent chooses pairs of items to combine, and the selected pair, if a valid recipe, then results in a new item that is added to the table. We see here that to create paper plane, the agent first creates paper by combining wood and pressure, followed by bird and metal to create airplane. Finally, paper and airplane are combined to yield paper plane. The agent also created an irrelevant item, origami, at the second step. Agents can optionally be penalized for making such irrelevant items and rewarded for creating useful intermediaries. The task difficulty can be varied by changing the number of distractor items not used in creating the goal, or by varying the task depth. As the number of possible paths of item combinations grows exponentially with the difficulty, effective WordCraft agents must make use of common sense knowledge to target the most likely combinations for creating each goal. The agent is trained on a subset of such tasks, with the ultimate goal of being able to generalize to tasks containing unseen goals or recipes. WordCraft also runs fast, achieving speeds of up to 8,000 environment steps per second on a single machine. We assess the difficulty of the task and the importance of common sense understanding in the following experiments. We first investigate how far we can go by simply incorporating prior knowledge encoded in the form of pre-trained word embeddings. To make our agent invariant to table size and item position, we use a simple self-attention actor-critic model, in which the goal and currently selected item are transformed into a query matched to keys for each table item. The policy logit for selecting each item is then the corresponding self-attention score. We compare a semantics unaware model, representing items as random vectors, with a model that represents items using glove embeddings. The model using glove embeddings significantly outperforms the semantics unaware model when evaluated on zero-shot performance to unseen recipes, matching human-level performance. Next, we see if we can further improve the performance of our agent by incorporating information from a knowledge graph representing either the full set or a subset of recipes. We construct the recipe graph by connecting items with two types of edges, representing whether items combine in a recipe and whether they are involved in producing a specific goal. We then train Complex, a state-of-the-art link prediction model, on the relations in the recipe graph. Once trained, Complex can then score how likely it is that any given relation exists in the graph. At each time step, we use Complex to produce score vectors representing how likely it is for each table item to be a component of the goal, as well as combine with any already selected item. We then linearly combine these score vectors with the policy logits using learned mixture weights. We find that with a single distractor, an agent with a full knowledge graph model achieves superhuman zero-shot performance on unseen recipes, while agents with only a partial knowledge graph model performs on par with glove-only agents. With more distractors, partial knowledge graph agents begin to see improved sample efficiency, but final generalization accuracy is still on par with a glove-only agent. As next steps, we're excited to explore how agents can jointly reason over common sense knowledge and its own lifetime experiences by using recurrent policies and external memory representations. We're also excited to introduce new modalities such as control and images into WordCraft, as well as explore how we can condition on text corpora. We're also open sourcing the code of this environment and the baselines on GitHub, to allow the community to explore this new benchmark. Thanks for listening.